Okay. Thank you very much for having me. This is a real pleasure to participate in this program. And so I want to talk a bit about what we're doing in my laboratory to identify chemicals of emerging concern in environmental samples. And so in this case, we're really going to do a pretty deep dive into the technologies that our laboratory applies in order to really answer this question: which organic pollutants occur in the ambient environment? And I would put it to you that in the science of exposomics, as we try to map out what exposures are most relevant for human health and environmental health, one of the critical questions that we need to ask is how can we actually map these complex mixtures that we are all exposed to. And so this is really made challenging for those of us who are environmental analytical chemists by the fact that we really are facing a scenario with vast chemical space. Okay, so chemical space is really vast, and the question is, how can we assess which chemicals in commerce are most important as emerging contaminants in the environment, the aquatic environment, as well as others. And so this is also made challenging by the fact that chemical use and production and regulatory lists are incomplete. And then also, this is really a complex mixture that's made more complex by all of the chemical transformations that happen in the environment, in aquatic environments, and runoff from the environment, and wastewater, in air, and in the atmosphere. And so this really combines to make prioritization of compounds in environmental exposures more difficult, and also by proxy, this makes compound identification in analytical studies really, really challenging, because we're faced with an enormous number of possibilities and a limited amount of chemical and spectral data that we can use to solve these problems. And then, of course, this is made really almost sort of unapproachable on a sort of human scale by the fact that we are trying to analyze and identify mixtures of thousands of compounds simultaneously in these environments. So the question that we really have been approaching is, how do we implement a strategy that goes from mass spectrum to chemical structure? How do we implement this spectrum to structure workflow in the laboratory in a routine way? And so I would sort of compare and contrast how this work is done in laboratories by mass spectrometrists. First, the sort of standard interpretation procedure is that we would identify a molecular ion for a compound we might be interested in. We would assign a molecular or empirical formula using monoisotopic mass, isotopic abundances, and other sorts of resources. And then we would postulate possible structures. Possible structures that might explain this chemical, annotate fragmentation spectra, and then rank those structures. And so this is the sort of thing that an expert mass spectrometrist would do, one compound at a time. But the challenge in doing this on a scale of the exposome is that there are many possible adducts, there are many possible formulas, and critically, there are thousands of molecular features that we find in environmental samples. And so manual interpretation and annotation is just not feasible. So our hypothesis is that we can leverage computational mass spectrometry approaches to efficiently assign both molecular and structural formulas for micropollutants and environmental contaminants in environmental samples. So it goes without saying, in our laboratory and in most of the laboratories that do this work around the world, ultra high resolution mass spectrometry is really the enabling technology for this kind of work. And so I'm not going to dwell on this, but I do want to note that recent advances really in the last 5 years, which have increased resolution to close to 500,000 in some cases, and most importantly, mass accuracy, such that we can define masses of contaminants that we're finding in the environment down to less than a part per million. This is really the way that we have been able to move into these high throughput and high coverage non-targeted analysis methods. And so we're leveraging this in our laboratory on a routine basis. So this is sort of the roadmap of how we actually assign compound identification confidence when we are doing annotations on a large scale. This is a scale that was essentially, that was published by Emma Szymanski a number of years ago, and it really lays out a roadmap for assigning confidence based on evidence and data requirements that we can collect for compounds of interest in environmental samples, such that level 1 confirmed structure compounds are those that we're most certain about. We can actually compare our spectral data to reference standards that we have in our laboratory, and we can confirm structures. And so we can go down through decreasing levels of annotation confidence all the way down to level 5, where we really don't know much about the molecule other than its exact mass. And so the devil is really in the details of how we actually leverage the data requirements that we collect to arrive at probable or tentative structures. And so what I want to do here is talk about these two levels, level 2 and level 3, probable structure annotation and tentative structure annotation for environmental contaminants, because that is really the area where we stand to gain the most in terms of knowledge of samples, but also it is the more difficult set of annotations to arrive at. So let's focus in on this sort of level 2 structure, probable structure annotation. So critically, what we need here is library spectra, so mass spectra that have been compiled for reference standards, or we need some kind of diagnostic evidence to prove this. So we've attempted in my laboratory to maximize success in being able to annotate at this probable structure level. And the way we do this is pretty simple. We just need to increase the number of and the quality of MSMS library spectra that are available for this non-targeted analysis. And the way we did this was that we combined the 3 largest compiled and curated mass spectral libraries. That is the NIST mass spectral library, the MassBank open source mass spectral library, and the more proprietary MZ Cloud mass spectral library. And we put these together, especially MassBank and NIST, into sort of a funnel of sort of data processing, such that we could take all of these spectra and combine them into a single workflow. And most critically, during the process of this, we used some computational mass spectrometry tools to annotate these spectra in order to know something about their quality. So we wrote some custom software to put all this together into a complete database that we can then query using software with our own mass spectrometry data. And so what we end up with is a total non-redundant spectral library size of about 46,000 individual compounds. So that's not the number of spectra, that's the number of unique compounds that are covered by this total library. And the data actually is of some varying quality, and I'll get back to that in a minute. Here is sort of a snapshot of the combined library. So 46,412 compounds. What's interesting is if you break down the distribution of compounds among the 3 component libraries, what you see is that the libraries are highly complementary. So the intersections here, you see that only less than 10% of the total compounds are present in all 3 libraries. NIST, MassBank, and MZ Cloud are quite complementary. NIST by itself contains almost 20,000 unique compounds in that library. And so what you can see is that we get great benefit by putting all of these libraries together and being able to query them together. One real challenge, though, is how do we query using a single type of mass spectrometry data that we might acquire in our laboratory using a specific type of instrument? How do we query that against libraries that are composed of spectra from various provenance, some from different laboratories, some from different instruments? And one of the things that we were able to really take a look at here was the performance of the various library spectra that are in these component mass spectral libraries. And what we see is if we break this down by mass analyzer type, Orbitraps versus, for example, QTOFs here, you can see that there's a wide range of mass accuracies that are inherent to the data. And so this was really critical for us to then take our computational mass spectrometry tools and annotate these spectra in order to break them down into classified data quality bins, and then be able to use those assigned accuracies to actually inform our search algorithms, so that we are setting mass accuracy thresholds spectrum by spectrum, so that we're increasing the veracity of our matches. Okay, so we incorporate this into a total workflow. In addition to the libraries, we've built an R package called CDUtils, which actually is incorporated and complements some of the commercial software that we use, in this case, Compound Discover software, which allows us to do things like align, detect, and then consolidate our features to get rid of artifacts in the data. So the example here is that in this specific analysis, the raw data coming out of our commercial software is giving us about 3,300 features, or what's called compounds by this software. If we process that through our dereplication algorithms, we're able to reduce that down to less than half of that number of features as actual compounds. And this is getting rid of in-source fragments, things like adducts and other kinds of artifacts that might occur. And this allows us to winnow down and prioritize the features in the mass spectrometry data that we are most interested in with respect to identification. And then we can pass that into some data extraction algorithms that we use to then pass the data into both the library searches as well as into some of the computational mass spec tools I'll talk about in a few minutes. So how does this perform? Well, so this is just an example where we used the EPA's Environmental Non-Target Analysis Collaborative Trial, or NTACT, mixtures to test our combined libraries. And in this case, we were able to achieve almost 600 unique library matches out of these mixtures across all of the different chemical mixtures that were provided by the EPA. And you could see that in this case, there's a lot of differences between the mixtures that they sent us, and that was, of course, intentional. So when we combine all this together, we get a very high annotation rate, actually. And this was actually our most successful annotation that we were able to achieve of all the strategies that we used for analysis of these mixtures. And so obviously, I'm not going to read through all 600 of the compounds that we identified, but here's just a snapshot of the top 50 most abundant library matches that we had. The scores, the library scores, are over here, as well as our mass error. And actually, this is something I want to point out. If we take a look at the distribution of mass measurement errors for our library matches, we can see that this really highlights the high performance of these technologies in order to, in terms of being able to measure mass very, very accurately. So this really confirms and lets us evaluate in real time in our data sets what our achieved mass accuracies for these compounds identifications are. And this was both in positive and negative ion mode for these compounds. So we're doing quite, I think, well for our library matches and our annotation based on library matches. But we still have, if we come back to this annotation confidence scale, we still have the question, what about all of the other components that might be present in these mixtures? Typically, what we find is that using even our extended library matching approaches, we are only able to annotate less than 10% of our compounds that we observe in environmental samples at the level 2 probable structure point. So the question is, how can we do better? How can we annotate more of these compounds that might be relevant from a sort of exposure standpoint? And one way is to move down the list down here to tentative candidate annotation and do that in a reproducible way. So the question is, how do we improve our success in annotating structures for compounds for which we have no reference standards and we have no library spectra, curated library spectra? So now we are in the realm of sort of expert mass spectrometry interpretation. And so we literally, in this case, take a book or a page from the book of Fred McLafferty, Interpretation of Mass Spectra. And if we go back to this sort of seminal text, and we look at what our standard interpretation procedures are, we can actually come up with ways to use these steps to guide us in our computational mass spectrometry and cheminformatic approaches to automatically annotate molecules using mass spectrometry input. So our objective here was to build a model that combined both computational mass spectrometry using in silico mass spectrometry prediction and annotation software that use both combinatorial fragmentation algorithms as well as machine learning approaches which are able to match mass spectra to structures based on computational tools, as well as information on metadata of chemicals in databases. For example, numbers of patents, numbers of scientific references, and number of data sources in our databases in order to prioritize annotations of structures. So if we want to do this, we've sort of designed an overall non-targeted analysis workflow here where we take our mass spectrometry data, our raw data right off the mass spec that includes both MS as well as tandem MS data. We use this to sort of consolidate and annotate a molecular formula. We assign a molecular formula for this data. Then we query compound databases to come up with candidates, possible structure formulas from our molecular formulas. And then the task now is to rank those structures based on experimental data versus mass spectral predictions using computational mass spectrometry, and then combine that with information we can glean from our compound databases. Now, to do that, we've built an algorithm and software package called Painter, and this stands for Probability Assessment for Identification in Non-Targeted Environmental Research. And so the idea here is that we're leveraging multiple in silico mass spectrometry fragmenters together with things like compound metadata, and then all of the work that we do up front on our work to annotate these compounds into a generalized linear model that we can then use to score. So this is our scoring design. I'm not going to go through in great detail the complexity here, but the idea is that we query our databases, in this case PubChem, with a molecular formula to come up with a list of candidates. And then we score those candidates with our experimental spectrum using our algorithms here. So these are our computational mass spectrometry tools. These scores are then input into a generalized linear model for our fragmenter. We rescore our candidates and come up with fragmentation scores, ranks, and what we call delta S, which is a difference in score relative to the top ranked candidate. We then combine that with data on the number of sources, number of references, and number of patents for each of the structure candidates that we're evaluating. We build that into a second generalized linear model that combines the fragmentation data as well as the metadata, and then we have our model output that we then threshold based on a probability cutoff built from a false discovery rate determination with our data. If we evaluate this, we can evaluate these data compared to individual fragmenters. So this is sort of a step plot on the right here showing cumulative fraction correct in a test set of about 1,500 structures and spectra that we know the answer to. And in this case, actually, you can compare the cumulative percent correct for our model in red versus all four of the individual fragmentation algorithms, METFrag, MAGMA, CFMID, and CSI finger ID. What you can see is that although the individual fragmenters, some of them actually perform somewhat poorly by themselves, when we put them all together, right, you can see CSI finger ID does quite well by itself, but we do quite a bit better actually when we put all of these together in a model, a combined model, and then score. If we take a look at the actual performance of the model itself in terms of false positive and true positive rate, this is basically the ROC curves, receiver operator curves, and the separation in score distributions for both negative, so wrong answers versus right answers for our test set of 1,445 test molecules. You can see that as we, in the fragmenter only versus the fragmenter plus metadata, GLM results, you can see that we get better separation when we include the metadata into our algorithm. And so we get a true positive rate of 97%, a false positive rate of only 2% in this combined model. So it's performing quite well. If we take a look at how this actually is giving us results in our analysis of the NTAC samples, you can see that in this case, if we test versus our library matches that we generated using our combined mass spectral libraries, 62% of the time our in silico fragmentation algorithm actually gives us the same answer as our library top match and in 82%, we get actually the same formula. So just to kind of give you, I'm running out of time, but I'm going to give you an example of how we've used this in environmental samples. This is for indoor environmental analysis. We actually noticed a really interesting paper that came out of John Gysi's lab a few years ago, where they were able to observe a bunch of brominated compounds in house dust. But in many cases, they didn't know what the structures of these compounds were. They were able to assign masses and formulas, but they couldn't find the structures. So we actually took our algorithms and we were able to, in most cases in this table that they actually published in their paper, we went back to our own data, found the same compounds, and were able to use our algorithms to come up with postulated structures and confirm those for these azobenzene-based dispersed dyes. And so if we actually, the way that we annotate these, so we have our mass spectral data, our tandem MS data, we query for molecular structure candidates from our formula, and we can actually discriminate the correct answer here in green from all of the incorrect candidates in red based on our combined fragmenter scores. So we put these together into and use this approach to map our entire data set for our dust samples, and we were able to identify a number of different dispersed azobenzene dyes in these samples with high confidence based on both our metadata as well as all of our fragmenter data. And so we care about these compounds, of course, just for relevance. These are known mutagens, so they're mutagenic in the environment, and there's also indications that they cause contact dermatitis through exposure through textiles, through clothing, for example, airline personnel. So we're following up these compounds, but it's an example of where we're able to use these tools without spectral libraries to actually successfully annotate exposure-relevant compounds. All right, so I'll just conclude and say that if we combine, hopefully I've convinced you that combining computational mass spec as well as cheminformatics adds a lot of confidence to molecular and structural formula assignments. We can integrate all of these tools together into an automated data analysis workflow, and this makes it much easier to do annotation. And then if we combine our curated MSMS libraries with our statistical model for in silico spectrum to structure annotation, this allows us to actually boost our identification confidence, not only of the compounds that we are annotating only from our in silico work, but also allows us to boost the annotation confidence for our library matches based on concordance of data. Okay, so with that, I'll wrap up and thank all of my colleagues, and thank you for your attention.